Electron configuration and orbital diagrams. Today we're going to look at where the electrons actually live within an atom. The first thing we want to take a look at are energy levels. An energy level is also called an electron shell, and they are fixed distances from the nucleus of an atom where electrons may be found. Each row or period on the periodic table represents the total number of energy levels an atom has. Although we know that it's not a perfectly accurate model, you can think of the energy levels like rings around the nucleus, where each row on the periodic table adds a ring or grouping of orbitals around the nucleus. So if we look at this diagram here, we have the N in front represents the energy level, and so our first energy level, the one closest to our nucleus, so our nucleus with our protons would be in the middle, and our first energy level would be that first red ring there. The second energy level would be the purple ring, the third energy level the blue, the fourth energy level the green, and continue on from there. So each of those is called an energy level. We can also call it an electron shell. And that is the first way we divide the electrons in our atoms. Those rings or those energy levels will hold only a certain number of electrons each. So let's practice a few of our atoms and identifying the number of energy levels they have. So this first one says, how many energy levels does silicon have? So take a look at this periodic table and find where silicon is. Hopefully you found that it's number 14 right here. So we are going to follow across the periodic table to the left-hand column or left-hand side, and that labels the rows, also called the periods of the periodic table. So this is silicon is in period 3, so that means that it has 3 energy levels. So it would have 3 of those rings drawn around our atom, and that's where the electrons would occupy. So let's try another one. How many energy levels does tin have? Pause the video and find tin on the periodic table and try and identify how many energy levels it has. So hopefully you found that tin is number 50 right here. And when we follow it across, it is in period number 5. So it has 5 energy levels. Let's try another. So pause the video and find where zinc is and determine its number of energy levels. So hopefully you found zinc is number 30 right here. So that corresponds to period number 4, meaning that it has 4 energy levels where its electrons are. We also can say that it has 4 occupied energy levels. That's typically languaging that we use for chemistry. All right, one more to try. How many energy levels does helium have? So helium is number 2 on our periodic table, and it is going to correspond with the first energy level. So it has 1 energy level. So that's going to be the first thing we want to identify about our atoms is how many total energy levels they have. So now we're going to take a look at the orbitals that are within those energy levels. So we've seen that atoms have separate energy levels that build from the nucleus out. And within those energy levels, it breaks down into what are called orbitals. So the first orbital we're going to take a look at is called the s orbital, and it has a spherical shape. Now our s orbital, each of them can only hold 2 electrons. So we can see down here that they're each labeled 1s, 2s, and 3s. The number in front is going to represent that energy level. So the 1s orbital would be within that first energy level, and it's an s orbital. So that would hold in that sphere 2 electrons. Now, once we have that, that's not that many electrons, so we're going to need more space for electrons. Well, we can go to the second energy level and add 2 electrons into another s orbital. We can go to the third energy level, and this would hold another 2 electrons, and it would keep going for each period on our periodic table. We get an energy level, so we go 4s all the way up to 7s. Now, that's only 14 electrons, so that's not that many. We're going to need more places to put our electrons. So our s orbital is pretty basic. It can only hold 2 electrons. But we're going to see what the other shapes are and how many electrons they can hold. The next orbital we get is called the p orbital, and I call it the peanut orbital because it kind of looks like a peanut. But these can hold 2 electrons as well in each what we call suborbital for a total of 6 electrons. So the p orbital is one set of p orbitals is all 3 of these. Now you can see that we've got a little x, y, and z labeled there because they follow the x-axis, the y-axis, and the z-axis is where they line up. Now, all of them have the 2 in front, so these would all be on the second energy level, okay? So all 3 of these would be in that second energy level, that second ring on our periodic table. And then when they overlap, we get something like this. Now, each of these can hold 2 electrons. You're noticing probably a pattern here where we get sets of 2 electrons. Okay, and we'll talk about why they come in pairs like that. So we get 2 electrons. So as a whole, the p orbital can hold 6 electrons total. So we can get 3 p electrons, so that would be 6. We can get the 4 p electrons, that would give us 6 more electrons, 5 p, and that would give us 6 more, all the way up to 7 p. Now, this one starts at the second energy level. There is no 1 p orbital, all right? So our first one, we have 1s, 2s, 3s, 4s, continues up. Then our next one, we start at the second energy level. So we have 2p, 3p, 4p, and keeps going up all the way up to 7. Okay. So you might guess where our next one starts. So this is our p orbital, and we can hold 6 electrons. So that adds a lot more electrons to our atoms, but still not enough. So we're going to keep going. And here is where it starts to get a little crazy looking. So this is called the d orbital. I remember d orbitals, I think of it like a dime because it can hold 10 electrons and a dime is 10 cents. So that's just ways we can kind of remember these things. They're not the actual names. So the d orbital has some really funky shapes to it. Now, these would all start on the third energy level. So we'd start with 3d. These would all be on the third energy level. And each of these shapes would, again, hold 2 electrons. So with all of these shapes, we'd get a total of 10 electrons, okay? So those would all be on the third energy level. When we go to the fourth energy level, that fourth ring, you can add another set of these d orbitals. So we'd have 4d and 5d and 6d, etc. Okay, so we can keep adding those d orbitals as we go. So we've got, so far, we've got our s orbital. We've got our, that holds 2 electrons. We've got our p orbital, which has 3 what we call suborbitals that each hold 2 electrons. Oops. So that gives us 6 total. And now we have our d orbital, which has 5 suborbitals, which each hold 2 electrons, giving us 10. So that gives us a lot of electrons that we can put and place into our atom. And we're building from that nucleus out. Now, our very last shape of our orbitals is called the f orbital. I call it the funky orbital because it has all kinds of crazy shapes to it. And again, these all hold 2 electrons. So there are 7 shapes here. So this whole thing would hold 14 electrons. So it has 7 suborbitals or shapes to them, and it would hold 14 electrons total. So this one starts on the 4th energy level. So we'd have 4f for all of these, and they would follow different planes on our axes there. So you'd have 4f and 5f and go from there and build up. All right. So our s orbital starts on first period, our p starts on second, our d starts on third, and f starts on the 4th. Now that's a lot of information, all of these different orbitals with their shapes, but it does correspond to our periodic table, which makes our life a lot easier. So go ahead and take some time and use some colored pencils or some highlighters, something that you can shade in lightly so you can still see your periodic table, the one that's given to you there, and make sure you fill in the little key on the side with the colors, okay? Yeah, I believe Yours might be slightly off. Well, let me check on that. I feel like 2 of the letters are reversed. You can start filling that out and getting your color coding. Yep. So make sure when you do your key down here, I flipped these two, the D and the P, okay? But make sure it corresponds to what you do in the table there. All right, so you can flip them that way. So the way this works, after you've maybe pause for a second and then get it color coded and then come back, okay? So now that you've got it all color coded, the way this works is our first 2 columns represent our s orbital. Okay, so as we get to each row, we're going to start by adding electrons to the s orbital. Now, this helium, I know it's way over here, but it's color-coded yellow because it kind of fills in this gap right here is how we think of it. So it actually is an s orbital. Now, you'll notice and remember that the s orbital holds 2 electrons, and this columns are 2 elements across. So we're going to add 1 electron there, and then the second electron there, and that fills up our s orbital with electrons. And it only has the s orbital in the first period. You'll notice we only have yellow in that first period. Now when we get to period 2, we also have an s orbital, so that's our 2s orbital. Oops, 2s. And then when we go across over here, we're getting to that p orbital. So this first row would be our 2p. And remember that the p orbital has 3 shapes to it, and each of those can hold 2 electrons, so that's 6 electrons. Well, guess what? It's 6 elements across. So each one of those, as we go through, we're going to add another electron for each element. Then when we get to the third period, we've got our 3s, and we go across to 3p, and we come down to the 4th energy level, we get 4s. And here is where it gets a little funky. We're going to take a look. This is actually where our d orbital starts, but it's 3d. So we're going to see why that's weird in our atoms. But our periodic table corresponds to our orbital shapes. Down here, the green section is your f orbital, those 2 rows. Remember, those 2 rows fit right into, oops, not right there, right into our periodic table right there. And so we kind of get that funky thing going on with F. Now, we won't have to deal with the F orbital in this class, so don't worry too much about that one. That kind of overcomplicates things. So we'll stop at element 56 in this class. We won't go beyond that one. Okay, let's take a look at what's going on with this and how we deal with it. Now, if you flip up on your paper, you'll see this same diagram, and this just helps us kind of visualize what's going on here. So let's just review it. We've got that 1s orbital that holds 2 electrons, and that corresponds to that first energy level, that red energy level there, okay? Within that second energy level, we're going to have the s orbital and the p orbital. So each of these circles that you see on the right side here holds 2 electrons. So we can hold 2 here, plus 2, 4, 6, 8. We can hold a total of 8 more in our p orbital there, or in our second period there. So that's 10 electrons total. In our third energy level, we've got the s orbital, the p orbital, and the d orbital. So we can actually hold up to 18 electrons in that third energy level. And then that fourth energy level, we continue building, and we get the s, p, d, and f orbital, and you would get, let's see, 32 electrons total is what we could fit there. So you can see how we can start building up these big atoms and adding all these electrons to it that they need. Okay, so that kind of gives you an idea of how it corresponds together. So we want to be able to write what's called an electron configuration. Okay, an electron configuration works as an address to identify where all the electrons in an atom are located. So it's giving all the locations to us. We build the electron configuration from the lowest energy level to the highest one needed for that atom. Okay. The electrons are added to the orbital shapes in a specific order, which corresponds to the periodic table. And we can use what are called orbital diagrams to help us in kind of getting started and writing electron configurations. So up here on the top, this is an electron configuration. This is our electron configuration for fluorine. So the way I would read this is 1s2, 2s2, 2p5. So we're just reading through left to right. Now, each of these chunks represents some of the electrons in that fluorine. Okay. Now, it follows this pattern. The number in front is your energy level. So the 1 and the 2s are the energy levels. The letter represents the shape. So those S, P, D, and F orbitals. And then your exponent is the number of electrons that belong in that orbital. So 1s2 means the first energy level s orbital holds 2 electrons. If I look at 2s2, it means the second energy level s orbital holds 2 more electrons. And the last part says 2p5, so the second energy level p orbital has a total of 5 electrons. So we could actually add up the electrons, so 2 plus 2 plus 5 would give us 9, and if you look on the periodic table, number 9 is fluorine. So that's a way we can actually identify these elements. So we want to be able to write those electron configurations. Now there are a few rules that we have to follow when we want to write an electron configuration. The first thing is an energy level is filled with electrons before going to the next energy level. Also, an orbital shape, so S, P, D, or F, is going to be filled before going on to the next orbital shape. So we can't have things half done. Now, third thing, if an orbital has more than one shape, so our P, D, and F orbitals, each suborbital, so each one of those shapes, is filled with 1 electron each before they go to the second electron. And this occurs because it's more stable for the electrons to spread out if they can, and then start pairing up. So I kind of think about it this way. So you're in your house, right? And you've got, say you've got 3 bedrooms, okay? And you've got a bunch of siblings. So you're the oldest, so you add to the first bedroom, right? These are the kids' rooms, right? And then you have a little brother or sister, so they go in the next room. And then you have another little brother or sister, so they go in the next room. When that 4th kid comes along, they got to pair up. So now we're going to have a pair of kids in a room. And if another sibling comes along, then we're going to start pairing them up again. Okay, so that's how electrons also add to our atoms. They want to spread out before we start pairing them up. And that's when we deal with our P, D, and F orbitals. Okay, so we'll see how that works in our diagram as well. So we're going to start really basic with hydrogen. We're going to just start building some of our atoms. We'll skip a few here and there, but we'll just start at the beginning so we can get an idea of how this works. So we're going to do what's called an orbital diagram first. So that's going to be this first part, and then we're going to use that to write our electron configuration. Okay, so we're going to first locate our atom on the periodic table. So hydrogen's our first element. So remember, those first 2 columns on our periodic table are known as our s orbital. So we're starting with 1s. So in that 1s orbital, hydrogen only has 1 electron. Okay, so we're going to add that first electron to the 1s orbital. So the way we do that is we just use little arrows. Okay, you can do a full arrow, or a lot of times you'll see that they're drawn as a little half arrow, just because that's how they draw them. So that is our whole orbital diagram for hydrogen, all right? Just 1 electron. Now, if we wanted to translate that into our electron configuration, we'd write this part first. So in the 1s orbital, hydrogen has 1 electron, all right? So really basic for our first one. It's going to start making more sense as we go through more examples. Okay, let's take a look at helium. So helium's over here, but remember it kind of fills in this space right here. So helium has 2 electrons, but they're both in that first energy level. So we don't need any of these 2s2p. So we're going to add the first electron, and then we're going to pair it with a second electron. And we use a little down arrow to represent that. Now the reason we use these 2 arrows is because the electrons within that 1s orbital, or within any of these, are going to spin in opposite directions. And that's why we can have 2 negative things hanging out together. It's that spin that allows them to occupy the same space. So in that first energy level, we get 2 electrons. So we translate that into 1s, and there are 2 electrons. So helium's electron configuration is 1s2. Let's try another one. So let's move on to lithium, our very next element. Now you can notice we're going down to that second energy level, okay? So what does that mean? Well, we've got to go through everything and to get to lithium. So we're going to start on that first energy level, and we've got to take care of those first 2 electrons. So 1s has 2 electrons. And then lithium is going to end at that 2s, and it has 1 more electron. So lithium has a total of 3. So there's our 3 electrons. So the way we'd write this is 1s2, 2s1, because there's 1 electron in that. Our exponents, 2 and 1, add up to 3, which is our number of electrons on lithium. All right, we're going to keep going. Try another one. All right, we are going to do this for boron. So we're going to jump ahead a little bit. We're going to skip beryllium for now. So we got to get to boron. Now, this is like going through a map. We've got to trace all of our steps. So we got to go in order till we get to beryllium. Now, beryllium has 5 electrons. So I'm going to start with my 1s and do my 2 electrons there. I'm going to go to my 2s, my 3rd electron, my 4th electron, pairs it up. Now I'm in the p orbital, and I'm going to fill in my 1 electron there. So that gives me 5 electrons total. So to translate this into its electron configuration, we're going to say 1s2, 2s2, 2p1. And again, the electron or the exponents add up to 5, which is our number of electrons in boron. Okay, so our diagram and our electron configuration. So this is an address where we would find all of those electrons for boron. So let's just take a look at its model. If we had those protons in the nucleus, that positive nucleus, our first energy level would have 2 electrons on it. And that second energy level would have a total, we'd have the 2s and the 1p, we'd have 3 electrons on that second one. Okay, so this is kind of how these two things can relate to each other, right? So we've got those 2 electrons in that first energy level and those total of 3 electrons in that second energy level. So that's another way we can think of this. All right, let's try another one. So we're going to jump to oxygen. So oxygen's over here. There's a red line in it. And it is number 8. So we need to add 8 electrons to our orbital diagram. So again, we're going to start with 1s. And we're just going to start adding pairs of electrons, and that takes care of that. Then we go to 2s and add our pair. So we've taken care of 4, we have 4 more. Now when we get to this p orbital, this is a set, right? It has 3 suborbitals or 3 subsections. So again, just like the kids in a bedroom, we want to spread them out first, and then we start pairing them. We need 1 more electron, and that gives us our total of 8. So that is our proper electron configuration for oxygen. So let's see how we would write it. In the 1s orbital, there's 2 electrons. In the 2s orbital, there are 2 electrons. Now, in our 2p orbital, we're going to total up all of our electrons. So 2p has a total of 4 electrons. All right, so that's our orbital. And if we go through this, we could say, okay, hydrogen and helium, that's our 1s2. We've got our 2s2, and then 2p. We go 1, 2, 3, 4. It's the 4th element over, right? So we can find oxygen based on that as well. All right, let's take a look at another one. All right, we're going to go all the way to neon. Neon over here. All right, so again, we need 10 electrons. So we're going to fill them in. We're going to do 1, 2, 3, 4. We're going to separate them now. 5, 6, 7, then pair them in our suborbitals, 8, 9, 10, and that fills our orbitals that we have so far. So we translate that into 1s2, 2s2, 2p, and their total of 6 there. Now neon hangs out on this end, and we call these the noble gases. Okay. Noble gases. These are noble or special because their orbitals are full. So when you get to their p orbital, it's always going to end in a p orbital. It's always going to be p6. All right, we're going to fill them up there at the end of the row. That's going to become important when we look at kind of a shortcut version of this, and you'll look at that on your assignment. Okay, let's keep going. All right, we're going to do magnesium. We're going to jump to number 12. Now you'll notice I added some more space here for our electrons. So 12 electrons. We got 1, 2, 3, 4, 5, 6, 7, separating them, then pairing them, 8, 9, 10, 11, 12. So that fills up those orbitals. So now you'll notice, if we look at magnesium, it's in the third orbital, and those first two columns are the S section, and it ended in 3s. So where it's located is going to tell you what your last section is going to be. Okay, so we've got 1s2, 2s2, 2p6, 3s2. And that's our electron configuration. All right, let's try another one. All right, we're going to take a look and get to sulfur. Now, I'm going to try and show you guys how to do this without our orbital diagram. All right, we're going to check out how to do this without the orbital diagram. So if we're just given our periodic table and we want to write the electron configuration and don't want to have to draw the whole diagram, what do? Okay, well, we use our periodic table. So we're going to start in period 1. And so we're going to write 1. That first section is our s orbital. And that's the first elements we come to. And there's 2 across. So 1s, 2. Then that takes care of the first energy level. So now we're going to go to energy level 2. We're in the s section. And it's 2 elements across. So 2s2. And we continue across our periodic table. We're still in the second energy level, and this is our P section over here, so 2P, and we need to fill that up, so that's 6 across, so we're going to put a 6. And we're going to continue, third energy level, S orbital, 2 across. We continue across the periodic table to third energy level, the P section. Now we only need to get to sulfur, so that's the 1, 2, 3, 4th element, so 3p4. And that would be our electron configuration for sulfur. Now you could also do the orbital diagram, and you would find that it's the same thing. So we can use either as a tool to help us out. Okay, now we're going to take a look at one that has the d orbital. Okay, so we're going to take a look at manganese. That is down here, number 25. So we need 25 electrons. That's a lot. Let's use our orbital diagram to help us out. So here's 1, 2, 3, 4, separating them, 5, 6, 7, 8, 9, 10, 11, 12. Into our p orbital, separating them, 13, 14, 15, 16, 17, 18. 4s gives us 19 and 20. We need 5 more. So they were in the d orbital. We're going to separate them. 1, 2, 3, 4, 5. Now, something you'll notice is that we are building, right? We've got 1s, then we got 2s, 2p, 3s, 3p, 4s, and then it goes back to 3d. So this is the weird thing that happens in atoms. And this is not something we made up. This is just what we have observed in atoms. Those d orbital electrons, because we're adding potentially 10 more electrons, that is way too many electrons for an atom to hold on the outside energy level. Okay, what we call the valence electrons. Those are the outside energy level. So instead of that, the atom's like, hey, these are too many. I'm going to put them in another energy level because it's going to be more stable for me. So it adds it to the previous energy level. So even though this is the 4th energy level, when we get to the d orbital in this section, it drops an energy level. So this would be the 3d row all the way up to here, and then we go to 4p. So we got 4s on this side, 3d, 4p. We do the same thing down here. We do 5s, 4d, 5p. Okay, so it's just going to drop one energy level when we get to that d orbital. Okay, so if we were to translate this into our electron configuration, we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. That is manganese. So they start to get a little longer when we get more electrons. But like I said earlier, we won't go beyond number 57, okay? Because it gets weirdo after that. Okay, let's check out one more. All right, for our last example, again, we're going to try it without our orbital diagram, just to use our periodic table and see how it works. So I'm just going to do a little labeling. These first two columns are S. This section over here is our P section, and our ones in the middle are a D orbital. We've got our energy levels on the left. So we got to get to astatine, or excuse me, not astatine, arsenic, AS. So that's number 33. So we're going to start at the beginning of our map up here at energy level 1. And we start in the S orbital, and then there's 2 elements across, so 1s2. That takes care of that first energy level. Then we go to energy level 2. We start in the S orbital, and again, 2 elements across, so 2s2. We continue across, still in the second row, second energy level, second period, but now we're in the P section, and there are 6 elements across, so that holds 6 electrons. We're going to keep going, third energy level, S orbital, 2 elements across, so 3s2. We go across the periodic table to over here. We're going to be at 3p, and again, 6 elements across, 3p6. We're going to keep going. We got 4. We're going to always start with that S orbital when we're on the left side, and it's 2 across, so that's S2. Now we hit the D orbital. Remember that that one drops in energy level. So instead of labeling it 4s, we're going to label it 3d. And this one is 10 elements across if we count them through. So that holds 10 electrons. All right. Now we're almost there. We're going to go back to energy level 4 because we've already used 3p. So now we're at 4p. And arsenic is the 1, 2, 3rd element. So 3p3. Or excuse me, 4p3, excuse me. So again, if we added up all the electrons in the exponents, that should add up to 33. So we've got 2 and 2 is 4, and 6 is 10, plus 2 is 12, and 6 is 18, and 2 more is 20, and 10 more is 30, and 3 more is 33. So that is our electron configuration of arsenic. That's our last example. So we're going to be doing some examples in, or some more practice on this in your homework. So you've got some with the orbital diagram. Those ones have boxes instead of just lines, but it's the same idea. And then writing your electron configuration from that. You've also got some practice where you're given the electron configuration and then you're trying to identify what element it is. So there's a couple ways you can do that. You could add up all the exponents and then find what number it is. Or you could follow the path of our periodic table like a map and find which element it is. Or you can look at the very last piece, and that's going to also tell you where it is. So if I looked at that piece, I'd say, okay, I'm in energy level 4. I'm going to go to my P section here on the right side, and it's the 3rd element over, 1, 2, 3. And that gives us our location of those last electrons that are added. So there's a couple ways to do that. At the end of your practice, it's also going to show you how to do the shortcut method, or what we call the shorthand method of this. So when we get these long elements, how do you write them a little bit shorter? So it'll explain that, and you'll practice a few. All right, you guys got this. Let me know if you have any questions. Thanks.